Okay, so we have already gone through two examples. In the first one, we were calculating the average speed and instantaneous speed of a falling rock. And in the second one, we were calculating the average rate of change of a population of Drosophila and instantaneous rate of change, say on one particular day. And in calculating these instantaneous values, that is instantaneous speed, the speed of the falling rock at an instant of time, or the instantaneous rate at which the population of Drosophila is increasing on a particular day, in calculating these values, we went through a limiting process in which we were calculating the average values over shorter and shorter intervals, and then we were trying to see where these average values are going, whether these values are going near some value, and that some value we defined to be the instantaneous value, instantaneous speed, instantaneous rate at which the population of Drosophila is increasing. Now we want to see what that limiting process is in this next example. Say, in this example, it has been phrased somewhat differently. How does the function, so now we are not looking at an application or a real world situation, but rather we are concentrating on a mathematical function itself, because in those applications also we had to deal with functions. So you look at this function, which is a rational function, a quotient of two polynomial functions. The numerator is the polynomial x square minus 1 and the denominator is x minus 1. It is linear polynomial, the denominator is. Now it is being asked, how does this function behave near x equal to 1, not at x equal to 1? Because you can clearly see that at x equal to 1 the function is not defined. That's because the denominator will become 0 if x is 1, which is not allowed. Division by 0 is not allowed within the system of real numbers where we are right now. But we can of course ask how the function behaves near x equal to 1. Okay, so let us start the solve, because it has been asked as a question, so, or rather as an exercise, a problem. So there is a solution. The function f(x) is not defined at x equal to 1, and everywhere else on the real line it is defined, because for no other value of x other than 1 is the denominator 0. It will be non-zero for x other than 1. For any real number x not equal to 1, we can simplify the rule of the function like this. So you can factorize the numerator as x plus 1 times x minus 1 divided by x minus 1, because x is not equal to 1 and hence x minus 1 is non-zero. So this x minus 1 and x minus 1 cancel out, and when you are cancelling such things, you should always make sure that the thing you are cancelling, the term you are cancelling, is non-zero. Now here, due to this condition, it is non-zero. So this is x plus 1. So although the function looks like this, actually it is just this. But keep in mind, the function is f of x equal to x plus 1, but x is not allowed to be 1. If we just simply write just this formula without this condition, then that is not this function, because in this function without this condition x equal to 1 is actually a point in the domain. For us, however, x1 is not a point in the domain of f. So the graph of f is the straight line y equal to x plus 1, but definitely not the entire straight line. From this straight line, one point will be removed, namely the one for which x is equal to 1 is the straight line, and when x is 1, y is 2, because 1 comma 2 is a point on this line, and that line will not be there in the graph of f. Everything else will be there with the point 1 comma 2 removed. Okay, so let us now draw the graph. So this is our usual x-axis, this is the y-axis, this is the positive direction of x-axis, the positive direction of y-axis. Here we have the origin. So we just have to draw. First of all, let us just simply draw the line y equal to x plus 1, and to draw it you just need 2 points, because you already know that this is a linear equation. So it's the figure is going to be a straight line, it represents a straight line. So when we put x equal to 0, then y should be 1. That means 0 comma 1 is a point, or yeah, okay, we can just simply understand what we are doing. So this much is 1, and when we put x equal to minus 1, y is 0. So minus 1 comma 0 is another point, so which is this point, say. Then our line looks like this. It extends on either direction without any bound, because that's what straight lines are. However, we are not drawing the straight line itself, but the graph of f. So this point has to be removed. 1 comma 2. This point has to be removed, and this removal is indicated by drawing a white circle like this. This indicates that the point 1 comma 2 is not a part of the graph. So this is our 1, and this y value is our 2. Now with this point removed, this line, or rather I should not say it a single line, but these two lines combined, they give us the graph of f. So this is the graph of y is equal to f of x. And don't write the graph of y equal to x plus 1, because that is just the entire line where the point 1 comma 2 is also there. So this is the graph. Now what we have been asked in this question is, what is the behavior of the function fx near 1? Now near 1 means two things. You can either be near 1 by being to the left of 1 or by being to the right of 1. So let me just arbitrarily take a point near 1 but to the right of 1. For this particular point, what is the y value? We can just simply look at the graph and see what the y value is. So this is the y value. I mean, the point on the graph corresponding to this x value is this, and the corresponding y value of course is going to lie on the y axis, and this is the y value. Which value, that of course would depend on the actual value of this x. Let me just write some x, say x1. It is some value of x which is close to 1 but lies to the right of 1, and correspondingly here we have got, say, y1. When x1 is close to 1 but still a little greater than 1, y1 is close to 2 but it is also a little greater than 2. What happens if we take a point, say, to the left of 1 that is also close to 1, say x2? Then corresponding to this point also we would get a y value, which again would come from the graph. So this one, this point, and this point is, say, y2. So whenever our x value is close to 1, no matter on which side of 1 it is lying, the y value also, it will either be less than 2 or greater than 2. It will also be close. And you can clearly see that if you slide this point x1 towards 1 further, then because the graph is like this, the y1 value will also slide and come down towards 2. It will be even closer to 2 than it previously was. Similarly, if your x2 values slides towards 1 from the left side, then due to the graph going like this, the corresponding y2 value will go up towards 2 and will be closer to 2 even more than how much close it is right now. So that's why we can say, or rather the authors have said this. Yeah, so this is the thing. So the exact thing that Thomas and Finney, yeah, it is just simply this. Even though I do not want to miss the phrases that they have used here. Even though f of 1 is not defined, one can clearly see that f of x, the value of f of x, gets arbitrarily close to 2 when x is sufficiently close to 1. That means, what that simply means is that you can make these y values y1, y2, these are after all functional values f of x. y1 is f of x1 and y2 is f of x2. These values get arbitrarily close to 2. That means you can make them as close to 2 as you want, by choosing your x values sufficiently close to 1. Okay, so that's what in this line the authors are writing. Even though f of 1 itself is not defined, we can see from the above graph that the value of f of x gets arbitrarily close to 2 as x is or x gets sufficiently close to 1. So you can make f of x as close to 2 as you want by choosing x sufficiently close to 1, which is clear from the graph itself. However, you can note that you can never make f of x equal to 1, equal to 2. F of x can never be made equal to 2 just because it becomes 2 or it would have been 2 had 1 been an element in the domain, a point in the domain, which it is not. 1 is not a point in the domain. So it's impossible to achieve 2 itself, but it's possible to be as close to 2 as you want. Although from this figure you can see that this white circle has some radius. So it may seem that before reaching 2, at some distance from 2, this line has stopped, but no, that's not what we mean by this drawing. This drawing indicates, or rather this white circle indicates, that this line, this broken line, this part of the line is actually getting close to 2, as close as it wants. Okay, we have just removed one point from the entire line, not this circle from the entire line. Okay, just one point has been removed. So that is why this half can get as close to that missing point as possible, and the upper half also can get as close to the missing point as possible, 1, 2. So that's what we have written here, and because of that, fx value can get, or y value can get arbitrarily close to 2 either from this side or from that side by making x sufficiently close to 1. And sufficiently close or close enough to 1, same meaning. And when to express this, we say I have already written what the authors have written in the next line. So I just simply write, we express this fact by saying that 2 is the limit of f of x as x approaches 1. It's like calculating the instantaneous rate of increase of the population of flies on day 23, I think it was. So that day 23 is 1 and the instantaneous rate is 2. Although here it's not rate, but I'm just simply saying analogously the value which corresponds to the instantaneous rate there, here that value is 2, approaches 1. In symbol we write like this. Limit of f of x is equal to 2 as x tends to 1, or this. You can of course ask, why am I not writing x plus 1 here? But I can write x plus 1 here. However, we choose to write the actual expression for the function which shows that 1 is not a part of the domain of the function. So you see one important thing, that the function itself need not be defined at the point at which we are calculating the limit, because for example here the limit of the function at x equal to 1 is 2. However, 1 is not a part of the domain. It's not necessary for the point at which you are calculating the limit to be a point in the domain of the function. However, it should be the case that your input values can get close to that point. So that provision, that situation should be there. Although 1 is not a point in the domain of this function, but the input values can be made close to 1. So they should be very close to 1, because otherwise we cannot, this just does not make sense that x is approaching 1. If x cannot approach 1, then it will not approach 1. Now, to show numerically what goes on here, or rather to show this thing, to express this writing numerically, some values have also been given by the authors, which are just simply these. It's presented as a table. However, there is no need to draw an actual table. You can just show the values. Values of x above 1, on this side we have values of x, and on that side we have values of f of x. Values of x below 1 and above 1, and on this side still not creating a table, but we can however separate them with a line. And on this side we have our f of x, which is x plus 1, but with the condition that x is not equal to 1. Okay. Now alternately, values of x greater than 1 and less than 1 have been taken, and the corresponding y values or fx values have been given here. So when x is 0.9, it is just 1.9, and when it's greater than 1, say 1.1, then this is 2. You just have to add 1, that's it. Now if you make this value, which is close to 1 but less than 1, even closer to 1, then you say take another 9, then your corresponding fx value gets a little closer to 2 than 1.9 is, because it is 1.99. On the other side, you can make this value a little more close to 1 by taking say 1.01. Then this value will get more close to, or not the exact this value, but in that case the corresponding value will get closer to 2 than this one is. So some more values. When it is 1.01, this one is 2.01, and then 0.999, then this one gets even closer, 1.999, than this one, to 2. On the other hand, if we continue to make this even closer to 1, this one also gets closer to 2 than even the previous value. And the last two values, I think they have taken many places of decimal, 6 nines. And correspondingly, the fx value looks like this, which is much closer to 2 than this one is. Similarly, if one considers this value, which is close to 1, much closer than this one, then the corresponding value also gets much closer to 2 than this one is. Okay, have I taken the number of decimal points correctly? 1 2 3 4 5 6 4 5 6, yes. So these values clearly show what we have claimed there, that the fx value can be made arbitrarily close to 2 by choosing x close enough to 1. Now based on all of these, there is this next definition, which is a definition of limit, but it's informal, and the definition goes like this. So this definition will be called informal definition of limit. There is a reason for it to be informal that will be discussed afterwards, and the definition is this: let fx be defined on an open interval be defined on an open interval around some real number x naught, say, except possibly at the point x naught itself. That means, okay, we are coming to the meaning afterwards. Let me just first finish writing. If fx gets arbitrary, yes, for all x sufficiently close to x naught, yes. If fx or f of x gets arbitrarily close to L, where L is some real number, just like x naught, L is also some real number. For all x sufficiently close to x naught, then we say that L is the limit of f of x as x approaches x naught, or how the authors have written here, we say f approaches the limit L. The limit L as x approaches x naught, and we write the symbol, that symbol, limit symbol. And we write like this: limit of f of x is equal to L as x approaches x naught, or x tends to x naught. Okay, now let us dissect this definition. Okay, we already know what is happening, but still there are some fine points to which I want to draw your attention. Let fx be defined on an open interval around x naught, okay, except possibly at x naught itself. If fx gets arbitrarily close to L for all x sufficiently close to x naught, we say that f approaches the limit L as x approaches x naught, and we write that this entire thing in symbols like this. Now if you see the situation in a graph, say, although there is no need to draw a y-axis here, but still I am drawing. So there is some graph of our function, but keep in mind what is being said here: fx is defined on an open interval around x naught. So before anything happens, our point x naught is given, it's some point on the x-axis, and an open interval around x naught, that is an open interval in which x naught is a point. Say that open interval looks like this. X naught is not necessarily the midpoint, it is there somewhere in this open interval, and this is the domain of f, this open interval. Now something else has also been said, that fx is defined on such an open interval except possibly at x naught itself. It may be the case that f is not defined at x naught, that can happen, just like the previous example, example 5, in that this open interval is the entire real line and x naught is the point 1. So our f is defined throughout the interval except at 1. But it may also be the case that f actually is defined at x naught. It may be defined at x naught, it may not be defined at x naught. Correspondingly, x naught may be a point in the domain of f, it may not be a point in the domain of f. That's why the authors are writing except possibly at x naught itself. Now if one tries to draw the graph of the function and say the situation is like what we had in the previous example, say x naught is not a point in the domain, f is not defined. Now the graph will, we don't really know how the graph will look because f is general, but it will be some curve or something at least. Say it's going like this, and say this is the graph. The graph cannot touch this line because open interval, the boundary points of an open interval are not points of the open interval. Also it will not touch this line, but that's not the important point here. The important point here is that this is a situation just like that one, fx equal to x square minus 1 divided by x minus 1. Now the point that is missing from this graph is this point, which is x naught comma L. Some point is missing from this graph. Let that point have y coordinate L, that means this is L. So this is L, okay, and now you can see that the situation is just like the previous one. So what we are saying is that if fx gets arbitrarily close to L, as for all x sufficiently close to x naught, how close do you want to make fx to L? That depends on you. Say you say that I choose one area around L like this, okay, just like there is an area around x naught which is represented by this open interval. Say you have chosen an open interval in which L is lying, and you want to make your fx value close to L in the sense that you want fx to be lying inside this interval itself. It should not get outside, it should not get that far from L. For you, this being in this interval, whether it lies above L or below L, if fx lies inside this interval, then you say, okay, I am satisfied, fx is close to L. According to me, this is what I mean when I say close to L. So say your fx lies here, okay, then for that fx, you of course should have your x this. For this fx, x should lie here, okay, but can you identify some area around x naught so that it can make sure that whenever you are choosing your x value from inside that area, your fx value will lie within this interval. Yes, you can choose. You just look at the boundary, where the boundary of this open interval is indicating on the graph, and this boundary also, the lower boundary almost touched the lowest point of the graph, but anyway you understand that it's a little on the right side. So if I just simply drop two lines, then you have got one further open interval that also contains x naught, but now if your x is coming from within this open interval, then the corresponding f of x lies within this open interval, and hence according to the definition of your close, fx is close to L. However, note that if your x goes outside this smaller open interval, say this is your x, then your f of x may not lie inside that pre-chosen interval around L. So this becomes your f of x if this is your x and it lies outside that interval, so according to you it is not close to L. And what happens is that you can this interval is your choice. That means how close, that is your choice. You can make this as small as possible, as small as you wish, making sure that L lies inside this. This is our L. No? L lies inside this interval. Then you should be able to find an interval around x naught, so that if your input comes from that interval, then your output lies in that interval around L, so that your condition of closeness is satisfied. When that happens, we say that the limit of fx is L as x approaches x naught. That is why we write things like this. If fx gets arbitrarily close to L, this arbitrarily close means it is your choice how close you want fx to make, how close you want to make fx to L. I think I butchered the sentence, no? How close you want fx to be to L. Okay, that is your choice. For that, you should be able to choose x sufficiently close to x naught. Also look at this, for all x sufficiently close to x naught. For all x sufficiently close to x naught. To this side, also to that side. So in this informal definition itself, I have actually given you the exact definition to which we will come later. Okay. Now why is this definition informal? That is because these phrases arbitrarily close to sufficiently close, they are vague phrases. They are not mathematical phrases. Arbitrarily close means how close? For example, if I choose this interval and say this is my close to L, for me means this. Someone else may choose an even smaller interval and say that, okay, for him or her, close to L means that. They will not recognize my close as close enough. And in fact, the authors have said something very nice in this regard. The authors say this definition is informal because phrases like arbitrarily close and sufficiently close are imprecise. Okay, they are subjective, just like any adjective is. Their meaning depends on the context. And then they say, this part I really like, to a machinist, someone who is constructing a machine, manufacturing a piston, close may mean within a few thousandths of an inch. For a piston engine, for example, the piston engines that you have in high-end cars, say supercars, they have to be extremely precise, and for them close or precision means being accurate within a few thousandths of an inch. For a machinist, that's what close means. However, to an astronomer studying distant galaxies, okay, close may mean within a few thousand light years. To an astronomer, a few thousand light years here and there, that does not make any difference. So for an astronomer, that may mean close. So for an astronomer, this may be close. For a machinist, this may be close. So that's why we should somehow quantify these phrases, and that's what we do in the exact precise definition of limit, which is going to come. But fortunately, this intuitive and easy to understand definition itself is enough to calculate many limits. We will need the precise definition when we will prove laws or rules of limit. Okay. Now let me give you, or let us go through the next example, which actually has three functions given to us, and which will reveal, or which will rather emphasize this particular point, that the point at which we are calculating the limit, it need not be a point in the domain of the function, but something else is also there. So let's look at example 6. In example 6, without writing much, there are three functions that are given. One of them is our f itself that we saw in example 5. This is f, but there is another function g, I think it's g. Now gx is defined like this. Part of gx is just like fx, when of course x is not equal to 1. But unlike fx, gx has a meaning at x equal to 1 also, and its value has been defined to be equal to 1 when x is equal to 1. And one more function is given, which is hx. And hx is just simply x plus 1. Now let us draw the graphs of these functions. The graph of this function, of course, we have already drawn, so we know how it looks. We can quickly draw it. So say this is our 1, minus 1, 1. And the point that we have to remove is this one. So I am drawing the circle rather large. I mean, from the distance that I am looking at this, it is rather large, but for you, I should draw it at least this large. Okay, so this is the graph of y is equal to f of x, and this is the point 1, which is not a point in the domain of f, and this is 2. What about g of x? For g of x, the graph is somewhat similar with only one difference. Again 1, minus 1, 1. And this point is not there. This point is not there on the graph, but in its place something else is there. Note that unlike fx, gx is defined at 1 and g of 1 is defined to be equal to 1. So we have this situation. So the graph of the previous function f is these two broken lines. The graph of g is these two broken lines, but with this single point. It's like someone has knocked this point out of the graph of the straight line y equal to x plus 1, removed the point and got rid of it completely. So that is the graph of fx. The graph of gx is that point simply has come out of this place and it's now situated here. Okay, so this is again 1. This is 2. And the graph of hx is that entire line, because the h is just the function x plus 1. So we are going to draw that also, although we know what it is, but still. Here it's one continuous line with no break or no damage. So this is y is equal to g of x, and this one is y is equal to h of x. Okay, so the graphs make sense, and now we can clearly see from these three graphs that in all of them the limit is actually 2. Because as x approaches 1 or as x is close to 1, f of x is close to 2 in all of them, in spite of these functions having different behaviors at x naught, at 1. So we write we can see that f, g, h all approach to as x approaches 1. But the difference is this: f of 1 is not defined. That is one thing. What about g? g of 1 is defined, but defined means g of 1 is 1, but the limit of g of x is 2, which is not equal to g of 1, because 2 is different from 1. So that means the limit of g at 1, the limiting value of g at 1 is different from the value of g at 1. Okay, limiting value at 1 is one thing, and value of the function at that point 1 is an entirely different thing. In this case, the value at 1 is not there at all. Here it is there, but it's different from the limiting value. H of 1 is also defined, and in this case the limiting value at 1 and the value of the function at 1 are both equal, and both of them are equal to 2, because h of 1 is 1 plus 1, that is 2. So this difference may be there, and this difference also proves that the limiting value of a function at a point actually does not depend on what goes on at that point, but rather what goes on near that point. That we can see from these three examples clearly. In spite of these three examples having differences at the point 1, but they behave exactly the same near 1. So that's why the limit of all of them is 2 as x approaches 1. X approaches 1 means we are concentrating on the values of x near 1, not at 1. Okay, so that difference has been shown here nicely by these functions. And this type of functions where the limiting value and the value of the function, which is also defined, and these are equal, they are somewhat special, and we will see about them in section 1.5. So that will come. They have something to do with continuity. You can see, although I have erased those two graphs, looking at the three graphs, you can see that the other two are broken at 1. In the graph of f, the point that should have been there, had 1 been an element in the domain of f, that point is just simply missing. We have gotten rid of that point. In the graph of g, that still the graph is broken, but that point lies below. But the point is that the graph is broken near 1. It is not a continuous line. So this thing has to do with something known as continuity of a function. We will see about this. But you can clearly understand geometrically why that is called continuity. Okay, now the limits of this type of functions, where the limit actually becomes the value of the function, are of course quite easy to calculate. What you just have to do, you put x equal to 1, that's it. So the authors write like this: sometimes this f is not that f, okay, it's a general function f, can be calculated by calculating just f of x naught, that's it, and that is the limit. So we need to identify what type of functions behave like this, because calculating limits for them becomes an extremely easy task. So this happens for algebraic combinations of polynomials. This happens, for example, for or rather whenever f of x is an algebraic combination of polynomials. We already know what polynomials are, and by algebraic combination we just mean these things. Say you take the sum of two polynomials, or their difference, or their product, or their quotient. For such combinations this property is there, and so calculating limits is very easy for them. Or in fact even trigonometric functions have this property, and trigonometric functions for which f of x naught is defined. This has to be defined, of course, otherwise you cannot put the value of x naught in f. You encounter any algebraic combination of polynomials or trigonometric functions, or a mixture of polynomials and trigonometric functions, and say you want to calculate the limit of such a combination at x equal to x naught as x tends to x naught. If you put x naught in that combination wherever x is there, and there is no problem, that means a value comes out, that is, if x naught is a point in the domain of that combination function, then you can just simply know that the limit is f of x naught, that's it. And the next example shows just this, where several limits are written. For example, the first one is this: limit of 4 as x tends to 2 is 4. The 4 that you are seeing here is not just the real number 4, but rather the constant function 4, which is the function whose domain is the entire set of real numbers, and it's at every real number the value is 4. So that is not going to change. So if x gets near to on this side of 2 or on that side of 2, it's going to be just 4. Similarly, if we change the point at which we are calculating the limit, then also it's not going to change. And it's just simply this, because this function, the function looks like this: f of x is constantly 4 where x is a real number. So the point here is that the limit is f of 2 at x equal to 2. F of 2 is 4. Here the limit is f of minus 13, that is also 4. That's why. See, in C we have this. In this one the function is not constant, but it's the identity function, and it's just simply a polynomial. These are also, this is also a polynomial for a constant polynomial, this is also polynomial. So here the limit is just you evaluate the function at 3. At 3 the function has value 3, so that's why the limit is 3. Keep in mind that this fact that we have just stated here, that algebraic combinations of polynomials and trigonometric functions, for them limits can be calculated like this. We have to prove this fact. Now we are just simply seeing the use. The proof will come when the time comes. D, here you have the limit as x tends to 2 of what is the function? 5x minus 3, again a polynomial. So you just evaluate the polynomial at x equal to 2. 10 minus 3, which is 7. Then E, x tends to minus 2, and the function here is this rational function. A rational function is the quotient of two polynomials. Now before you put x equal to minus 2, you have to make sure that minus 2 is a point in the domain of this function, It is, because you can just simply put x equal to 2. Whenever you get a quotient like this, the only problem that may arise is from the denominator. If the denominator becomes 0, then the point that you are putting, which makes the denominator 0, is obviously not a point in the domain. Just like how we had in case of x square minus 1 divided by x minus 1. For that function, x equal to 1 is not a point in the domain. For minus 2, however, there is no problem. So here the limit is just simply this. So it becomes minus 6 plus 4, minus 2 in the numerator and 3 in the denominator. So this is the limit. And because we have seen quite a few examples, so let me just complete everything. In example 8, two basic facts are being stated, which are rather easy to see why they are true. If f is the identity function, f of x equal to x and x naught is any real number, or let me write the way I am writing, and x naught is any real number. Then we have this limit. It is just that one we have seen in the previous example, limit of x as x tends to 3 is equal to 3. To actually prove these statements and also the one about algebraic combination of polynomials, we need the exact precise definition of limit, which we so far have not got. The only thing we have got, we know so far, is the informal definition of limit. So right now we are just going on stating the facts, and later when we have the exact definition of limit, we will prove these things. But now, of course, to understand why these things are true, to just see why they are true, you can draw the graphs and see why they are true. If f of x is the constant function, f of x equal to k, where k is some real number and x naught is any real number, then limit of f of x as x approaches x naught is limit of k as it approaches x naught is equal to k, and which is that first one, limit of 4 as x tends to 2 is 4, and also limit of 4 as x tends to minus 13 is also 4. For these two claims, I want you to draw the graphs of this function, these functions, and then see, like how we saw today, why the limits are the things that are being claimed here. What happens near x naught in those graphs? And now let us see in this final example, what are the cases in which you may not have a limit, that is, limit may not exist actually. These are cases where we have seen that limit exists, but maybe it's the situation that as x approaches x naught, the values of f of x actually do not approach anything. In such cases, we say that the limit does not exist. Now we are going to look at 3 examples in this one example itself. Example 9. So 3 functions are given. In fact, it's it's given as a question. Discuss the behavior of the following functions as x approaches. Let me just simply write, discuss the behaviors of the following functions as x approaches 0, and the functions are these. The first one is u of x, and it's partly defined for negative real numbers. It's defined to be constantly 0, and for non-negative real numbers it's defined to be constantly 1. Then f of x, another f of x, or I think, this one is named g. Although it does not matter, but still some of you may be following the book, so it should match. G of x is defined to be equal to the reciprocal of x when x is not equal to 0, and 0 when x is equal to 0. And there is one more, which is the most complicated of these 3. Now, because of a lack of an exact definition of limit, the best thing we can do in analyzing such functions is to draw their graphs, which is what we are going to do. Zero when x is less than or equal to 0, and sine 1 over x when x is greater than 0. Okay, so let us now draw the graphs. In order to show everything together, I am going to draw two graphs side by side, the graphs of u and g. For u, the graph is going to be this. So when x is negative, the graph is the u value is ux is 0. So it is this line. But the origin itself is not touched, because at x equal to 0, the moment your input x becomes 0, it jumps to 1. And after that it stays constantly 1. And that's why, and this is 1, this function is called the unit step function. In transitioning from negative to positive, it has taken a step of size 1. Suddenly there is a jump. So this is the graph. And for g of x equal to 1 over x, here I will need the negative part of the y-axis too. And if one looks at some values, one will see that the graph is in two parts and the shape is somewhat like this. When x is non-zero, and when x is 0, then the value is 0. So there is this extra single point also, that is also a part of the graph. Maybe that's why it is called g, because we have got previously we got 1g, where from the line we broke one point off and dropped it a little distance below those two lines. Okay, so this is the graph of y equal to u of x. This is y equal to g of x, and the graph of this one, I won't be able to do justice to this, but still let me try. In the beginning itself, I identify how far above 1 is and how far below -1 is from the x-axis. So the nature of the graph, you see, when your input is non-positive, either negative or 0, then your output value is constantly 0. And here, unlike this case, the origin actually is taken on. F of 0 is 0, but to the right side of the y-axis, things go like this. And you have to understand, I have drawn it rather sloppily, but you have to understand that as you get closer and closer to the origin, it gets compressed more and more. So in a very small interval itself, it oscillates a lot, and the oscillation increases and increases without any bound. the closer you get to 0, the more quickly it oscillates. That means more frequently, I can also say the frequency increases. Somewhat far away from 0, the frequency is not that much. But as it gets closer and closer to 0, it oscillates like this, and the frequency increases and increases without any bound. And in all of these three cases, limit does not exist. Why? So, and we also need to see what happens when x tends to 0. So what happens near 0 to the function, say u? To the left of 0, the u values stay constantly 0. So as your input x is near 0 but to the left of 0, u of x is constantly 0. But as your input is near 0 but to the right of 0, the u value is constantly 1. So the ux values, although to this side they are approaching 0, but to this side they are approaching 1, overall they do not approach 1 value. So there is no limit, because if we want to have a limit, all the values should approach one single value. That is not happening here. Although one can say that 1/2 of the values behave one way and the other half of the values it behaves another way. So one can say that the left hand limit is 0 and the right hand limit is 1, but right now we have not got those concepts, so we are just talking about limit, and there is no single value to which all the values are approaching. So that's why in this case there is no limit, and the reason can be put in a short manner by writing this: it jumps. So that's why there is no limit. There is a sudden jump. In this case there is no limit, because as your x approaches 0 from the right side, the fx value gets larger and larger without any bound, and that's why the graph goes like that. It goes towards plus infinity without ever stopping anywhere. Whereas as your x approaches 0 from the left side, then also it becomes very large negatively. It drops below the y-axis and it drops without any bound, as if it's falling in a bottomless pit. So that's why in this case the situation is somewhat manageable, that the values were approaching some values but different values. That's why there is no limit. In this case they are not approaching anything. No real number is there to which the values are converging or approaching. So that's why here it has no limit, and here also it grows too large. That's what the authors have written. What is the problem here? And this is the graph of y equal to f of x. Here to the left of the origin, of course, you can say the left hand limit is 0, because it's just constantly 0. But on the right side, what happens? As you concentrate on an interval near 0, when you concentrate on the right side of the interval, the value, remember I said that the value increases or rather oscillates more and more frequently. So it does not settle anywhere. The values do not settle near a single point. They keep oscillating, and the oscillation becomes worse and worse, faster and faster, more and more frequency. So that's why here also there is no limit, because a single real number is not approached. And here this entire thing can be expressed by writing it oscillates too much. And with this section is over, and in the next calculus video we will be able to start solving the problems, the exercise problems that are there at the end of this section. So that's just it for tonight, and tomorrow we also have tomorrow we are going to go back to Galileo's group theory problem. So see you with that tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.